Here we have a double integral whose limits are not all constants. We can see that the upper limit for this integral is 1 minus x. We want the double integral of the function f of xy equals 2xy. Here is part of a graph of that function. Let's consider the region over which we are integrating this function. We're integrating from x equals 0 to x equals 1. And we are integrating from y equals 0 not to a constant, but to a value that depends on what x is. Okay, we're integrating as far as 1 minus x. So for example, when x is 0, we are integrating from y equals 0 to y equals 1 minus 0, which is 1. So when x is 0, the upper limit of this integral is 1 minus 0, which is 1. On the other hand, when x is equal to 1, the upper limit here is 1 minus 1, which is 0. So we are integrating from 0 to 0. Anyway, in general, y equals 0 is any point on the x-axis. So for example, for this point here, y is 0. Okay, so let's take a general point on the x-axis. So we are integrating from 0 to 1 minus x. Okay, we can see it over here as well. Anyway, we are getting the area under the surface from y equals 0, which is a point on the x-axis, to y equals 1 minus x. Okay, at this point y is 0, at this point y equals 1 minus x. So we are integrating in the y direction. Okay, we're dealing with increments of length dy along here. So we'll have the area of this cross section. Now y equals 1 minus x is the equation of a straight line. Because it's linear in x, we don't have powers higher than 1. And I've already explained how we got these 2 points. This point comes from letting x equal 0, this point comes from letting y equal 0 actually. You know, we can also quickly get an idea of the graph of this by comparing it to the standard equation of a line. The coefficient of x is the slope of the line, so the slope is negative, so it's sloping down the way rather than in the other direction. This value here is the y-intercept, the value of y when x is 0. We can see that it's 1, so we have straight away have 1 point on the line, and we know that it slopes down the way. That means if we pick any point on the line and go out, say, a distance of 1 is a convenient number, then we have to go down a distance of 1 because the slope is minus 1. We need to go down to get a second point on the line. To get the volume under the surface, we need to sum all these cross sections from x equals 0 to x equals 1. So that's where the second integral comes in. So we will have slices, not just cross sections, slices of width dx. Distance from here to here is dx, also shown over here. So we multiply the area of the cross section by dx to get the volume of the slice, as we saw in an earlier video. So there's the area of the cross section here, multiplied by dx to get the volume, and we sum all those slices from x equals 0 to x equals 1. Anyway, we do this problem like we did the previous problems where the limits are all constants. Let's take this inner integral. We have to integrate 2xy with respect to y, so we treat x as a constant. So we get 2x times a half y squared. Well, that's just xy squared. Okay, we apply our limits. So we plug the upper limit in for y now, because we are integrating with respect to y. So we have to take the upper limit 1 minus x and square it. Then we have a minus sign and we plug 0 in for y. Well, that's just going to give us x times 0, which is 0. Okay, you can see that we get a function of x alone, as we expect. And now we have to integrate that function of x alone with respect to x from x equals 0 to x equals 1. So basically we're summing up all these slices of width dx. Okay, I'm not going to bother trying to show it here, but you can imagine, roughly speaking, it looks like that. So we're summing all those. Okay, this is a straightforward integral. If you do this, the answer is 1/12. So that's the volume of the region underneath the graph of 2xy and over this triangular region. Next we are going to evaluate the volume under the surface given by f of x comma y equals 2x sine y over the region bounded above by the curve y equals x squared and below by the line y equals 0 for values of x lying between 0 and 1. So y equals x squared is a parabola passing through the origin. It's an increasing function of x, so as we go from over the x interval from 0 to 1, the curve is increasing. So here is the region that we are interested in, the shaded region here. The region is bounded above by this curve, so the region must be underneath the curve. So we are not showing the surface in this example. The z-axis is perpendicular to the screen, passes through the origin of course. We have this surface 2x sine y, which is actually above this region here. You see, for this region here both x and y are positive, and if you plug positive values of x and y into this expression you'll get a positive value for z. So the surface would actually be coming out of the screen to be above the screen, hovering above this region here, so I won't attempt to show that. Now we can consider a cross-section of that volume, a cross-section taken in the y direction. I'll show it in a different color here. So the y value of this point is 0, the point on the x-axis. What about the y value of this point? Well, it's given by the equation of the curve, which is y equals x squared. So this point here is x. Okay, x is some value lying between 0 and 1. So if this point is x, this point here has y value x squared. Well, I could just write it here. Well, it's already written down, but I'll just do it in red. So we have to get the area under the surface along the line y equals 0 to y equals x squared. So we're integrating with respect to y. And that's this integral in here. So here's the surface. That's the height of the surface above any point on this vertical line here. Again, that area is made up of infinitely many rectangles of width dy, because we're taking increments in the y direction, and the height is given by 2x sine y, as we've seen before. We multiply the height by the width to get the area of each rectangle, and we sum all those rectangles from y equals 0 to y equals x squared. So since we are integrating with respect to y, x is treated as a constant, so we just leave that to one side. It's multiplied by the sine of y. Now if we integrate sine y with respect to y, we get minus cos y, and our limits are from 0 to x squared. So we plug the upper limit x squared in for y to get this here, then we have a minus sign, and we have this quantity with 0 in for y. Well, the cos of 0 is 1, so we end up at minus 2x, which is plus 2x. Now, like we saw in the previous example, we have the area of the cross-section at any point x. That's what this quantity is, the area of the cross-section at any point x. And then we have to consider slices. Well, the slices will have width dx, and we multiply the area of the cross-section by dx. So this width here is dx. So area of the cross section times dx gives us the volume of each slice, and we sum all those slices from x equals 0 to x equals 1. Note that we can factorize 2x out of this expression. Note also that the derivative of x squared is 2x, so that suggests that we make the substitution u equals x squared, so we won't have to deal with a product of functions here. That's something we want to try and avoid that product. That u equal x squared, so differentiating du dx is 2x, du equals 2x dx, so you can see that we can replace the 2x dx with du, and instead of 1 minus cos x squared we have 1 minus cos u, so we've gotten rid of that product. And now we have a straightforward integral. The integral of 1 with respect to u is u. The integral of the cos function is sine. The integral of cos u is sine u. Now we need to change our limits. If x equals 0, you can see that u equals 0 squared. 0 squared is 0. If x equals 1, you can see that u equals 1 squared, which is 1. So as a matter of fact, the limits happen to be the same here. Okay, so we plug the upper limit 1 in for u. So we get 1 minus sine of 1. Then we have a minus and we plug 0 in. Well, we get 0 minus the sine of 0. Well, that sine of 0 is 0. So, of course, our angle is in radians. U is in radians here. So, to 4 decimal places, we get 0.1585.